In this section, we're going to cover in more detail AC motors and the different circuits used to reduce start, reverse, and decelerate them. We'll also take a look at some of the methods used for controlling the speed of the motor. In addition, we'll explain in detail the troubleshooting of single-phase and three-phase induction motors. So, let's start by reviewing the general operation of AC motors. AC motors are more commonly and widely used than DC motors in industrial applications and are available on three-phase and one-phase supply voltage systems. Most single-phase motors are less than 3 horsepower. On the other hand, three-phase motors are available in a range from a few horsepower all the way to several thousand horsepower. The three-phase motor, as its name applies, operates from a three-phase supply voltage. This type of motor is said to be an induction motor because the voltages, when applied, induce a magnetic field which makes the inside motor components rotate the shaft of the motor. You can remember how electrical power was generated from an alternator by transforming mechanical degrees into electrical degrees. Well, a motor does the opposite. It transforms electrical degrees into mechanical degrees, which are seen when the motor's shaft is rotating. Three-phase AC motors, as we'll see later, are also represented by the Y and delta configurations. They perform the inverse function of an alternator or generator system. The three-phase induction motor is primarily composed of these three basic parts: the stator, the rotor, and the end plates, which form the brackets of the motor. The stator is the stationary part of the motor, and therefore its name, and consists of several parts, including the frame type, according to NEMA standards. The stators consist of a group of individual coil windings where the rotor will rotate once the voltage is applied. These windings will be connected to the motor starter terminals. The rotor, as its name implies, is the rotating part of the motor and is constructed from either coils of wire wound on laminated steel, or it can be made from all laminated steel without any wire coils. If a motor's rotor has wire coils, it is called a wound rotor motor. A laminated motor rotor, which is most popular nowadays, is called a squirrel cage motor because the design resembles the cage used for pet hamsters and the like, and therefore its name. As you can see, there are no brushes to pass current to the rotating parts, as was the case in a DC motor. The current is induced from the stator field to the rotor. The end plates or brackets house the bearings for the motor, which, depending on the size, will use sleeve-type bearings if it is a small fractional horsepower motor, or will use ball bearings if a large motor. Sleeve bearings require periodic lubrication, and some ball bearings in small motors will be what's called permanently lubricated, while the larger motor's ball bearings will require periodic lubrication. These end plates are mounted on both ends of the motor and are held in place by bolts and nuts tightened and secured to the stator frame. The squirrel cage Y-wound dual voltage motor has 9 terminal leads from the end of its coils for field connections. These terminals are numbered clockwise, starting at 1, 2, 3, and so on. The terminal connections T1, T2, and T3 from the starter are connected to the T1, T2, and T3 of the motor. The other connections are wired like this for a high voltage configuration. For a low voltage configuration, we would connect T1, T2, and T3 to the starter and also tie together with terminals 7, 8, and 9 respectively. Terminals 4, 5, and 6 will be tied together, essentially making a smaller Y. As you can see, a motor nameplate may indicate 2 terminal configurations, one for the low voltage and one for the high voltage. The squirrel cage dual voltage delta wound motor has 9 terminal leads. This 9-lead delta motor configuration also represents the terminal in number order in a clockwise direction, starting at T1, T2, and so on to T9. For a full voltage configuration, we would connect the terminals like this, where the T1, T2, and T3 terminals are connected to the motor starter T1, T2, and T3 connections. For a low voltage configuration, we would connect terminals 1, 6, and 7 together, 2, 4, and 8 together, and 3, 5, and 9 together. As we'll see later, if we interchange terminal leads, 1 and 3 will result in a change or revert the direction of the motor rotation from clockwise to counterclockwise, or, in other words, from forward to reverse. Single-phase motors are used most frequently in applications requiring a fractional horsepower motor, or in applications where there is a need for a motor and there is no three-phase power available. The single-phase motor also has a stator, a rotor, and the end plates which form the brackets of the motor. These components are very similar to the three-phase motors, except that it may have some additional components or other modifications. The stator is formed by two windings, namely a start winding and a run winding. The start winding is used because single-phase motors are not self-starting on their run windings like the three-phase motors. The start winding is formed by fine gauge wire and is used to create a very strong magnetic field to start the motor. The run winding is made of larger wire and ranges from 12 to 16 gauge wire. If, when troubleshooting, you cannot tell immediately which one is the starting and which one is the run winding, you may place an ohm meter and measure the resistance of the two windings. The one with the most resistance reading will be the start winding because it has more wire turns than the run winding. When the motor is first started, both windings in parallel are energized, and only the run winding will be on once the motor has achieved approximately 75% of its speed. The start winding will be out because a centrifugal switch will detect the 75% speed and disconnect the start winding. The rotor is very similar to the one in the three-phase motor and is also called squirrel cage for the same reason. The end plates secure the motor to the frame. The terminals in single-phase motors have a standard method of identification. They may have 4 or 8 terminals. If it is a dual voltage single-phase motor, the running winding will have 4 terminals connected like this for 115 volts or like this for 230 volts. The start winding may also show 4 terminals, of which 6 and 7 are connected together, and 5 and 8 go to power. Terminals 5 and 8 of the start winding are in general represented in red and black, respectively. If you are troubleshooting a single-phase motor because it is humming and doesn't start unless you rotate its shaft, then the cause of the problem is the centrifugal switch not operating correctly or an open in the start winding. There are several types of single-phase motors, the most common being the split-phase motor. Others are the capacitor-type motors. The split-phase motor is essentially the one we have been talking about, and which does not have any capacitors in it. This motor provides the lowest starting torque of all single-phase motors and operates only on induction to start and run. It is very inexpensive and is available in many frame types suitable for mounting in most machinery. The capacitor motor is a single-phase motor and can be anywhere from 1/8 horsepower to 10 horsepower and has an additional capacitor component in series with the starting winding. This capacitor helps the motor provide more torque at start than the split phase. Among most common capacitor motors, we have the capacitor start, the permanent split capacitor, and the capacitor start, capacitor run. The capacitor start motor has a capacitor added to the start winding, which will be cut off once the motor gets to 75% of full speed. A permanent split capacitor motor is one that has a permanent capacitor in the series with the start winding. This motor will keep both windings on during operation. The capacitor start, capacitor run motor is a modification of the capacitor start, which adds yet another capacitor in parallel to the start winding, which provides the motor with better torque characteristics when the motor is operating at full speed. At 75% of full speed, the starting capacitor will be cut off while the running capacitor will still be connected to the start winding to provide additional torque. This motor basically provides the capabilities at start of the capacitor start motor and of the permanent split motor at full speed. The speed of an AC motor is determined by the number of poles that form the stator and the frequency of the AC voltage coming into the motor. The operating speed, called synchronous speed, is equal to the frequency of the voltage times a constant of 120 divided by the number of poles of the motor. The result of this synchronous speed is given in RPMs. So, for a 60 Hz frequency, a 2-pole motor will operate at 3600 RPMs, a 4-pole at 1800 RPMs, and so on. This formula indicates that the only parameters that can be changed in order to vary the synchronous speed of the motor are the frequency of the voltage or the number of poles in the stator field. This is very much unlike the case of a DC motor, where a voltage variation to the armature or field would change the speed. In fact, if the voltage to a motor is not within 10% of the rated nameplate voltage, severe damage can occur due to overheating. This happens because the torque of an induction motor varies with the square of the applied voltage. So, if a motor is running at, let's say, 80% of its rated voltage, the torque will be 64% of that at the rated voltage. Induction motors run below the synchronous speed because of losses in the motor. These losses occur because the rotor lags the stator's rotating magnetic field, therefore rotating at a slower speed. This reduction is called slip and is represented as a percentage of the synchronous speed. In fact, slip is necessary for an induction motor to operate and provide torque. Most motors run at between 2 to 10% slip with no load. The initial current pulled by a motor when it is first started is called the locked rotor amperage, or LRA. It is so called because this is the required current that moves through the stator to start to move the rotor, which is at rest or locked at rest. As the rotor starts to move, current is induced and torque begins to build up. As the speed increases, the current required diminishes until full speed is achieved. At this point, the current required is maintained. This current is called the full load amperage, or FLA. The locked rotor current, or INRUSH current, at start is about 6 to 10 times that of the full load current. The rotor of an induction motor will develop full or maximum torque when the speed has reached between 70 to 80% of synchronous speed. There are two ways to start AC motors. One is across the line or full voltage starting, and the other one is using reduced voltage starts and accelerating the motor to full speed. Let's first look at across-the-line starts. Across-the-line starts are generally used in small and moderate-sized motor applications, where the torque, speed, and power requirements of the driven load generally permit a full voltage start. These starts can be implemented using manual or magnetic starters. In the manual starters, the contacts are operated by a mechanical linkage from the toggle handle or push button provided with the starter unit. While in the magnetic starter, the power contacts are operated by a coil. These starters switch the full voltage to the motor, which, of course, makes the motor pull all the locked rotor amperage at start. The across-the-line start method generally applies to all standard motors. There is no acceleration to this start method. This across-the-line start also provides 100% of its torque at start. The main advantages of across-the-line starts are that they are inexpensive, starters are readily available, installations are easy and simple to maintain, and they do provide maximum torque at the start. The main disadvantages are that they have a high inrush starting current, and the torque may not be reduced at start in applications which may require it. For example, in a conveyor application, if the motor is started across the line, the large torque may be too much during the start and cause a spillage of material. The main reason for starting an AC motor at reduced voltage before accelerating to full speed is to avoid the high inrush current created by the lock rotor start. However, there are additional benefits achieved by reduced starts, such as less electric power demand from electric power utilities and the wear and tear of switchgear equipment due to the large current pulled by the motors. This is especially true in locations where there are a lot of motors and they are starting and stopping with frequency. Reduced voltage starts provide smoother transitions in current,
torque, and speed of the motor. There are 5 types of reduced voltage starts: the primary resistor, auto transformer, WYE-DELTA, part winding, and solid state, each one providing advantages and disadvantages. All of these methods, except the WYE-DELTA, provide closed transition, which means that power to the motor is not interrupted. The WYE-DELTA start provides an open transition, which means that power is briefly interrupted between the voltage steps. The primary resistor uses a resistor which is placed in series with the motor starter power contacts. These resistors in this start method are called primary because they are connected to the supply side of the motor circuit. The resistors are removed by the bypass start contacts S1 after a time delay, as we'll see shortly. The primary resistor provides at start about 65% of rated voltage and a starting torque of 42% of the normal torque. The current at INRUSH is limited to 65% of the locked rotor current. This primary resistor start provides a rather smooth motor start compared to the across the line. When the motor is first turned on, full voltage is applied from the power contacts at the starter and voltage is created at the resistors, thus reducing the amount of voltage going to the motor. At the same time the motor is turned on, an on-delay timer is energized. The delay timer contacts drive the accelerating contactor, which controls the resistor bypass contacts. Once the time delay has elapsed, the bypass start contactor S1 will be energized and the motor will have the full voltage at its terminals. As we can see in this graph, the line current kicks back up for a short moment when the resistors are taken out of the circuit and the motor is applied with full voltage. The number of primary resistors could also be increased to provide the motor circuit with more accelerating steps. Each one would be controlled by a separate on-delay timer. The timing relay is generally set at around 3 seconds for a 2-point acceleration with only one resistor. If more accelerating resistors are added, they are set at around 2 seconds between steps. A note of caution: due to the amount of current passing through during start, primary resistors become very hot and can cause severe burns. So when troubleshooting this type starter, please be careful. The auto transformer reduced start utilizes an auto transformer represented by this symbol to start the motor. The auto transformer can be tapped at 80, 65, or 50% of the line voltage. This reduced voltage is the one passed on to the motor terminals. The auto transformer draws less current from the line than the primary resistor type and is well suited for reduced voltage applications of motors above 10 horsepower. This start also allows for adjustments of initial voltage by tapping a different voltage at the transformer. This type of start is also suitable for long starting periods. At 80% voltage, this method gives 64% of inrush current and 64% of normal torque. At 65% voltage, the current and torque are both at 42%, while if tapped at 50% voltage, the current and torque will be lowered to 25%. The starter circuit for the auto transformer includes 2 contacts which are used to bring the auto transformer online to provide the voltage to the motor. When the motor has had a partial start, the starter's full voltage contacts close to bypass the auto transformer and provide full voltage to the motor. The wiring diagram for the motor circuit may have 3 auto transformer legs connected in a Y configuration, or it may have an open delta type configuration. Note that the 3 voltages to the motor are virtually the same, and the 2-coil open delta configuration usually produces a negligible imbalance in starting voltages. The control circuit for the open delta configuration is the same as for the Y configuration. When start is pushed, the timer TR1 starts timing, and its instantaneous contacts seal the circuit. The starting contactor S1 is energized because there is continuity, and all the 3 power contacts associated with S1, which are connected to the auto transformer, close. As soon as contacts S1 close, contactor S2 is energized, thus closing the S2 power contacts which connect to the other end of power to the auto transformer. At this point, the reduced voltage from the autotransformer is applied to the motor. When the time delay has elapsed, the on-delay timer will be actuated and bring the motor circuit to full voltage. Note that while the timer's delay contacts are in the transition of going from open to closed, and vice versa, to energize contactor M1 and take out contactor S1, the contacts S2 are still connected to the autotransformer and form the only current path as a reactive inductor to the motor, so that a closed transition is maintained. This is obtained because the interlocking of coil S2 is kept by its own contacts. Remember, the S1 contacts are in transition. When coil M1 is energized, the contactor S2 is taken out by the opening of the auxiliary M1 contacts. Note that the motor starter contactor M1 and the starting S1 contactor are shown mechanically interlocked. The autotransformer is usually set for 65% tap at the factory, while the timing relay is set at around 7 seconds for the reduced to full voltage transition. This timing can obviously be adjusted in the field. The Y-delta reduced start, also called star-delta, is intended for use with Y-delta motors where the motor is started in a Y configuration and then switched to a delta configuration. As you can recall, three-phase motors are available in Y or delta configurations. These windings are internally connected, and the T1, T2, and T3 terminal wires are brought out of the motor for connection to the motor starter. The Y-delta motor has 6 leads, T1 through T6, brought out of the motor. No internal connections are made from the factory, thus allowing the electrician or technician to wire the motor in a Y configuration or a delta configuration. For example, in a delta configuration of a 208 volts motor, terminals T1 and T6, T2 and T4, and T3 and T5 are connected together to form the delta connection. The voltage between each phase is the 208. When the motor is connected as a Y, having terminals T4, T5, and T6 tied together, the voltage between the phases before the motor will be 208 volts. However, the voltage across each winding to the neutral in the motor will be 208 volts divided by 1.73, or 120 volts. The current and the torque in this Y-connected motor will be reduced to 33% of INRUSH current and 33% of normal torque, respectively. Remember that in a Y system, the line voltage is equal to the phase voltage times 1.73, while both the line and phase currents are equal. Conversely, in a delta system, both the line and phase voltages are the same, while the line current is equal to the phase current times 1.73. By switching between the Y and delta configurations in this motor, we can therefore control the reduced start voltage, thus also reducing the INRUSH current. This is simply done by interlocking the power circuit with additional contactors. The control circuit follows the same principle as the other reduced starts. When the start push button is pressed, the timer is energized and the M1 starter is also energized. The starting contactor S1 makes the connection through its own power contacts S1 and starts the motor in a Y configuration. Once the time delay elapses, contactor M2 closes and the motor is configured as a delta motor, thus having full voltage across its coils. The open transition occurs when the timer contacts are starting to disconnect the S1 contactor and the M2 circuit is not yet connecting the power circuit. The auxiliary contacts S1 keep this connection from happening. This very short delay is necessary to avoid a short circuit in the power system between L1, L2, and L3. The timer delay is usually set at around 10 seconds between the Y start and the delta transition. There is also a closed transition Y-delta configuration, which is available at an additional cost. These closed transitions include additional contactors and a resistor bank used for the implementation of the circuit. In this configuration, the contactor S2 is used to connect the motor in a delta configuration with a resistor in series with the T4, T5, and T6 terminals. This occurs as soon as the S2 contactor closes, right after the time delay and just before the S1 contactor is de-energized, thus not allowing a break in the transition. The resistors prevent the potential short circuit. Right after the S2 contacts close, the M2 contacts shunt the resistor circuit and connect the circuit in the delta configuration, taking out the resistors by de-energizing S2. The result is a starting reduced current of 33% of INRUSH and a smooth transition to full speed. Part winding is the least expensive of all methods of reduced starts. This type can only be used with part winding motors, which have two sets of identical windings. These windings are intended to be used in parallel. Most dual voltage motors, but not all, can be used as part winding as long as the lower voltage is used. The circuit used to control these starts is rather simple. Once the start is pushed, the M1 contactor closes and places the line voltage across one of the two identical coils. Once the time delay occurs, the other coil is brought online by the turning on of contactor M2. M1 acts as the starting contactor, while M2 acts as the accelerating contactor. Note that each of the windings in the parallel connections have their own overload protection. As you can see, the voltage is not reduced in this starting method. However, the INRUSH current is reduced to about 65% to 48%. The reason being that when only one set of windings is connected, less current is drawn because the resistance of the single winding is larger than the resistance of both windings when they are in parallel. Therefore, this starting method is also grouped as a reduced voltage start. One disadvantage of this method is that it is not suited for high inertial loads or loads requiring a long starting period. In fact, if this motor start is longer than 5 seconds, it will overheat. The standard time for the acceleration step set by the timer is between 1 and 1.5 seconds. Solid-state starters, also called soft starters, employ SCRs to implement the reduced voltage start. In this configuration, two SCRs are paired off to control the AC voltage of each phase. One SCR controls the positive swing of the voltage, while the other controls the other negative swing. The control of the SCR's gate is performed by other electronic circuitry in the starter. Essentially, the SCR's gate is controlled to let through part of the AC voltage. In this manner, the motor will see reduced voltage current. This type of reduced start control is very similar in principle to the operation of a DC speed drive, where SCRs are also utilized. However, in a DC control, the SCRs are used in a bridge rectifier configuration on each of the phases. The AC control is used only to let part of the AC voltage pass the motor. Solid-state starters also include current transformers to feed back voltage and current information to the starter's electronic unit. The starter usually provides contact closures to indicate that the full load current and full voltage has been achieved. This information may be utilized in other control circuits if other motors should be started once full speed is accomplished. Other features may include a contact trip indication of an SCR failure. In this case, the motor can be disconnected from the circuit. The solid-state reduced voltage starter energizes the full voltage contacts once it is at full speed and disconnects the SCRs from the motor circuit. Some starters may include the contactors and overload protection in the same control enclosure, in addition to the SCR control. The current in these reduced starters can be effectively controlled from 25 to 70% of the INRUSH current, while the torque can be adjusted from 6% to 49% of full voltage torque. These controls can be adjusted in the starter by modifying the potentiometer or a digital setting. The acceleration to full speed can be ramp adjusted from 1 to 30 seconds. In Part 2 of this program, we'll go over reversal of AC motors, several deceleration methods used to stop a motor, and how we can perform speed control. Then we'll cover in detail the troubleshooting of AC motors.